The Wellington bomber sat on the dispersal hard standing at RAF Mildenhall, its fabric-covered frame gleaming dully under the Suffolk moonlight on the night of the 3rd of April. 1941 Squadron Leader James Ward and his 5-man crew completed their pre-flight checks with the mechanical precision that came from flying together for 8 months. They'd done this 23 times before. Load up with incendiaries and high explosive, cross the North Sea, find the target, drop the bombs, come home. Tonight's destination was Bremen, one of Germany's vital industrial ports, and intelligence suggested the flak defences had been thinned out for operations elsewhere. Should be straightforward. What nobody mentioned during the briefing was the ongoing argument raging through RAF Bomber Command about the very aircraft they were climbing into. The Vickers Wellington had become the backbone of Britain's night bombing offensive, yet it remained deeply controversial amongst pilots who'd flown more conventional designs. The source of controversy wasn't the Pegasus engines or the defensive armament, it was the fabric. Whilst American and German bombers boasted all-metal stressed skin construction that gleamed with modern engineering confidence, the Wellington was wrapped in Irish linen treated with dope, stretched over a peculiar basketweave metal framework that looked more like something you'd find supporting a greenhouse than defending against cannon fire. Barnes Wallis, the engineer behind this unorthodox design, had endured years of skepticism from Air Ministry officials who couldn't reconcile his geodetic construction theory with their understanding of how bombers should be built. He'd explained it countless times. The interlocking lattice of light alloy members formed a structure where loads distributed themselves automatically across multiple paths, making the aircraft stronger than the sum of its parts. On paper, it worked brilliantly. In practice, every pilot who looked at those fabric panels rippling slightly in the wind wondered whether they were climbing into a death trap. Ward wasn't among the doubters. He'd felt the Wellington absorb punishment over Wilhelmshaven in February, when a flak burst had torn a hole through the port wing large enough to crawl through. Yet the bomber had flown home steady as a train on rails. Still, he understood why some crews requested transfers to Hampton's or Whitley's bombers that looked and felt like proper metal fortresses rather than elaborate kites. The engines coughed to life at 2100 hours, their familiar rumble drowning out any last-minute doubts. Within minutes, Ward had the Wellington rolling down the runway, the tail coming up, the main wheels lifting off English soil. They climbed into the darkness, joining the stream of bombers heading east. Navigation lights blinked off as they crossed the coast. From here to target and back again, they were alone in a sky that belonged equally to them and to the German night fighters prowling for exactly this kind of prey. Wallis's calculations suggested the geodetic structure could withstand battle damage far beyond what traditional designs could survive. Those calculations had been tested in wind tunnels, proven in mathematical models, and validated in static load tests that had impressed even the skeptics. But mathematics and wind tunnels don't shoot back. Tonight, over the industrial heartland of the Third Reich, those theories would face a test that no laboratory could replicate, a test that would either vindicate Wallis's radical vision or confirm every doubter's worst fears about sending men to war in fabric-covered flying machines. The first indication something had gone wrong came at 22:45 hours, still 30 meters from Bremen. The rear gunner's voice crackled through the intercom with forced calm. "Skipper, we've got company. Looks like a 110 Sabotage. A Messerschmitt Bf 110 night fighter equipped with the latest Lichtenstein radar that could detect bombers from over 2 miles away." Ward pushed the Wellington into a shallow dive, attempting to gain speed. But the twin-engine fighter had every advantage: speed, altitude, and a pilot who'd done this dance dozens of times before. The Messerschmitt opened fire at 600 yards with its forward-firing armament: 4 7.92 mm MG-17 machine guns and 2 20 mm MG FFF cannons mounted in the nose. The cannon shells, each weighing 134 Grs and traveling at 600 km, were designed specifically to destroy bomber structures. They didn't just puncture, They exploded on impact, sending fragments, tearing through anything in their path. The machine gun rounds, though smaller, fired at rates exceeding 1,000 rounds per minute, creating a stream of metal that could saw through control cables, hydraulic lines and fuel tanks with surgical precision. The first burst walked across the Wellington's fuselage from tail to midship. The fabric skin offered no resistance whatsoever. Rounds punched through both sides as if the aircraft were made of tissue paper. The distinctive sound, described by survivors as like someone rapidly striking a snare drum mixed with the crack of small fireworks, filled the interior. Ward felt the aircraft shudder, not from structural failure, but from the sheer kinetic energy of multiple impacts. The navigator hunched over his charts, looked up to see daylight, actual starlight, streaming through a line of holes that hadn't existed 3 seconds earlier. But the mess-mit pilot had made a critical error. He'd opened fire too early, burning through ammunition whilst warded through the Wellington into evasive maneuvers. The bomber might have been slow compared to a fighter, but it could turn tighter than most crews expected. Ward hauled back on the controls, standing the Wellington nearly on its tail, bleeding speed deliberately to force the messes to overshoot. The German pilot, committed to his attack run, flashed past and had to break away to reposition. That respite lasted 40 seconds. Then came the second fighter, a Bf-110 from a different staff that had been stalking them from higher altitude. This pilot was more patient, closing to 300 YD before opening fire. The concentration of fire at closer range was devastating. Cannon shells exploded against the geodetic framework itself, sending fragments of light alloy spinning through the interior. One shell detonated against a main spar, creating a percussion that rang through the entire airframe. Machine gun rounds stitched patterns across both wings, some passing straight through the fabric-covered ribs without hitting anything structural, others severing electrical cables and puncturing the fuel tanks in the wings. Then the flak opened up. Bremen's defenders had tracked them on searchlights and now engaged with 88mm guns, whose shells burst in preset patterns designed to box in bombers. Each explosion sent thousands of steel fragments outward at lethal velocity. The Wellington flew through 3 separate bursts, each one adding dozens more punctures to the growing collection. The aircraft bucked and yawed with each near miss, the concussion waves hitting the fabric skin like invisible fists. Ward's instruments told a story of systematic destruction. The airspeed indicator needle was dancing erratically, a severed PTO line. Oil pressure on the port engine dropped 10 pounds per square inch, then stabilized, suggesting damage to the external cowling rather than the engine itself. The compass spun uselessly, its fluid line compromised. Yet, beneath the chaos of failing instruments, Ward could feel something that defied every expectation. The Wellington was still flying normally. The controls responded precisely as they had 20 minutes earlier. There was no alarming vibration, no tendency to yaw or roll, no sensation that the aircraft was coming apart beneath him. The wireless operator, positioned amidships where the fuselage was widest, found himself in the surreal position of watching machine gun rounds enter one side of the aircraft and exit the other, passing through the empty space between structural members without hitting anything vital. One round had clipped his desk, sending splinters into his logbook. Another had punched through his parachute pack hanging on the wall. He could count 17 separate holes within arm's reach, each one surrounded by torn fabric that flapped in the slipstream. Yet the aircraft maintained altitude and heading as though nothing had happened. The first Messerschmitt pilot, having repositioned for another attack, came in again from the port quarter. He fired another 2-conned burst, roughly 120 rounds combined from cannons and machine guns. He watched his tracer rounds impact the bomber's fuselage and wings, saw fabric tear away in strips, observed pieces of the Wellington's structure breaking free and tumbling away into the darkness. In his combat report filed 3 hours later, he would confidently claim a Wellington destroyed, reasoning that no aircraft could absorb that level of damage and remain airborne. He broke away to search for new targets. Certain he'd just witnessed a bomber's death spiral begin, but the Wellington hadn't entered any spiral. Ward had felt the impacts, heard the terrible drumbeat of metal on metal, watched more warning lights illuminate his panel. Yet the fundamental integrity of his aircraft remained unchanged. This wasn't luck or divine intervention. This was geodetic construction doing exactly what Barnes Wallis had promised it would do. Each time a round severed one of the basketweave framework members, the load that member had been carrying automatically redistributed itself to adjacent members. The structure healed around damage like a spider's web. Break one strand and the web sags slightly but doesn't collapse because 50 other strands share the burden. The second mess's pilot, more experienced than his colleague, recognized something unusual. He'd destroyed 11 bombers in his career, and they all followed predictable patterns once sufficiently damaged. They lost altitude. They trailed smoke or flame. They developed pronounced yaws or rolls as control surfaces failed. This Wellington was doing none of those things. It was simply continuing toward Bremen as though annoyed rather than mortally wounded. He positioned for a third attack, determined to aim more carefully for the engines or the cockpit, components that couldn't possibly survive direct hits. His third pass added another 47 holes to the Wellington's collection, 3 of which passed within inches of Ward's head. One cannon shell exploded against the main spar directly behind the pilot's seat. The impact transmitted through the geodetic structure as a sharp crack followed by a ringing resonance. Ward instinctively checked the controls still responsive, the airframe still solid. The German pilot, now critically low on ammunition and fuel, watched his quarry continue flying and made a decision that would haunt his post-mission debriefing. He broke off and headed home, filing a report of probable destroyed rather than confirmed kill. The Luftwaffe's intelligence branch, the Oberkommando der Luftwaffe's Technical Assessment Division, had been tracking Wellington bomber specifications since 1938 when the first production models entered RAF service. Their analysts, most of whom had engineering backgrounds from Germany's prestigious technical universities, produced detailed reports that circulated through Fighter Command headquarters. These reports contained accurate information about the Wellington's wingspan, bomb load, defensive armament, and operational ceiling. But they also contained a fundamental misunderstanding that would prove catastrophic for German night fighter doctrine. Document reference OKLIC 3-412, dated November 19, 1939, described the Wellington's construction method in dismissive terms. The report's author, an engineer who'd spent years working on the Hankel 111's all-metal stressed skin design, characterized the geodetic framework as an antiquated approach more suitable for civilian transport than combat operations. The analysis continued, fabric covering provides virtually no protection against modern weapons. British reliance on this construction method indicates industrial capacity limitations rather than informed design choice. The conclusion recommended that pilots engaging Wellingtons should expect rapid structural failure after concentrated fire. This assessment reflected Germany's own design philosophy. The Luftwaffe had committed entirely to metal construction. The Junkers 88, Hankel 111 and Dornier 17 all featured aluminum alloy, monoco or semi-mononoke structures, where the metal skin itself carried primary loads. This approach produced aircraft that looked and felt substantially more robust than fabric-covered designs. When cannon shells struck German bombers, they created small, localized holes that didn't compromise overall structural integrity because the surrounding metal skin continued carrying loads. German engineers assumed British fabric-covered bombers would behave oppositely. That fabric would tear extensively from each impact, rapidly compromising the entire structure. Night fighter pilots received tactical briefings based on these technical assessments. Standard doctrine for engaging Wellingtons, as outlined in training materials from the Nachtiagula Training School at Schlesisheim, emphasized short, concentrated bursts aimed at the fuselage rather than extended fire patterns. The reasoning seemed sound. Why waste ammunition when fabric construction meant the target would disintegrate after absorbing a few dozen rounds? Pilots were taught to engage, fire briefly, then immediately seek new targets rather than lingering to confirm destruction. Visual confirmation was considered unnecessary. If you hit a Wellington properly, it simply ceased flying. This tactical doctrine worked perfectly against genuinely vulnerable aircraft. When Luftwaffe fighters engaged Armstrong Whitworth Whitleys or Handley Page Hamptons, both of which used more conventional stressed skin construction with fabric-covered control surfaces, the abbreviated attack pattern produced excellent results. Concentrated fire damaged critical structural elements, and the bombers either broke apart in flight or spiraled uncontrollably toward the ground. German pilots accumulated impressive kill counts, their combat reports filled with confident assessments of bombers destroyed after brief engagements. But Wellingtons kept flying home with damage that should have been lethal. Combat reports began accumulating inconsistencies. A pilot would describe scoring definite hits on a Wellington, watching fabric tear away, observing pieces separating from the aircraft, then admit losing visual contact before confirming the crash. Intelligence officers initially attributed these reports to inexperienced pilots or poor visibility conditions. The possibility that German technical assessments might be fundamentally wrong didn't feature in their analysis. After all, fabric was fabric, metal was metal, and German engineering expertise was unquestionable. The reports must be explained by pilot error, not by gaps in Luftwaffe intelligence understanding of British construction methods that were proving far more sophisticated than anyone in Berlin had imagined. Barnes Wallis hadn't set out to revolutionize bomber construction. His path to the Wellington began with lighter-than-aircraft craft, specifically his work on the R-100, airship between 1929 and 1930, that enormous dirigible 89 ft long and requiring 5 million cub-feet of hydrogen taught Wallis something crucial about structural engineering. Conventional methods weren't always optimal methods. The R-100's internal framework used a geodetic pattern, a series of intersecting spirals forming triangulated structures that distributed loads across the entire frame rather than concentrating stress at specific points. When the airship pitched or yawed in turbulent air, no single structural member bore excessive force because dozens of members shared every load simultaneously. Translating that principle from a hydrogen-filled envelope to a combat aircraft required solving problems that had never been addressed in aviation engineering. Traditional aircraft used longerons, long structural members running nose-toe-tail with formers and stringers attached perpendicular to create the fuselage shape. This worked adequately, but created obvious weak points. Severe battle damage to a single longeron could compromise the entire load path, potentially causing catastrophic structural failure. Wallis proposed something radically different: eliminate longerons entirely, and instead create a basket-weave structure where every member intersected with every other member, forming thousands of small triangles that interlocked three-dimensionally. The mathematics behind geodetic construction borrowed from civil engineering, specifically suspension bridge design. When a suspension bridge carries load, the weight distributes through cable networks where tension in one cable automatically adjusts to compensate for loads elsewhere in the system. Wallis applied identical principles to aircraft structures using light alloy members arranged in opposing spirals. One set helixing clockwise from nose to tail, the other set counterclockwise. Where members intersected, they were riveted together, creating nodes that could transfer loads in any direction. The result was a structure where damage to multiple members caused only localized weakness rather than progressive failure. The geodetic fuselage of the Wellington consisted of precisely 1.73 individual light alloy members, each one machined to exacting tolerances and heat treated to optimize the strength-tow ratio. These members weren't simple tubes. They featured carefully calculated cross-sections that provided maximum rigidity along their length whilst remaining light enough that the complete framework weighed less than a traditional longeron structure of equivalent strength. Every member connected to at least 6 adjacent members, creating redundancy that meant the failure of any single component reduced overall structural strength by less than 3%. What made this design genuinely revolutionary was its behavior under asymmetric loading, exactly the condition created by battle damage. When a cannon shell severed several geodetic members on one side of the fuselage, the loads those members had been carrying didn't concentrate on adjacent members. Instead, they distributed through the entire three-dimensional network, traveling through intersecting nodes to undamaged members potentially located on the opposite side of the aircraft. The structure automatically found alternative load paths without requiring any pilot action or mechanical intervention. It was passive damage tolerance built into the fundamental architecture. Wallis's colleagues at Vickers had initially dismissed the concept as unnecessarily complex. Manufacturing precisely machined components and assembling them into a three-dimensional jigsaw puzzle seemed far more expensive and time-consuming than simply riveting longerons and formers together in traditional fashion. But prototype testing revealed advantages beyond structural resilience. The geodetic framework was actually lighter than conventional structures of equivalent strength, improving payload capacity and range. It also proved easier to repair in field conditions. Damaged sections could be cut away and replaced without compromising adjacent structure, something impossible with traditional longeron-based designs where each member carried continuous loads across significant fuselage lengths. Ward brought the Wellington back across the North Sea at reduced speed, nursing the aircraft through air that felt subtly different than it had during the outbound leg. The fabric covering, shredded in multiple locations, changed the aerodynamic characteristics slightly. Nothing dangerous, just a minor increase in drag and occasional buffeting. When the airspeed climbed above 170 mph, they'd completed their bomb run over Bremen, despite the fighter attacks dropping their payload on the target before turning for home. The navigator had plotted their course using celestial navigation after the compass failed, and now the Suffolk coast materialized through the darkness ahead. The landing presented no difficulties. Ward set the Wellington down at 02:30 hours on the 6th of April with the same gentle touchdown he'd achieved on his previous 23 operations. As the bomber rolled to a stop on the dispersal hard standing, the ground crew cycling toward them in the darkness had no indication they were approaching anything other than another routine return. The Wellington's engines shut down, the propellers windmilled to a stop, and Ward's crew climbed out, stretching muscles cramped from hours in confined positions. Then the crew chief, Flight Sergeant Thomas Ricks, brought his torch beam across the fuselage and stopped walking. The beam revealed not just damage, but systematic destruction, a fuselage that looked less like an aircraft and more like a colander. He moved the torch methodically from nose to tail, illuminating hole after hole after hole, each one punched cleanly through both sides of the fabric covering. Where cannon shells had exploded against the geodetic framework itself, the damage was more severe. Twisted metal members, torn fabric hanging in strips, internal components visible through gaps that shouldn't exist in any flying aircraft. Chris initiated the standard battle damage assessment protocol. Every visible hole was marked with white chalk, numbered sequentially, and logged in the maintenance record with position and approximate diameter. This wasn't unusual. Most bombers returned with some battle damage. But as the count climbed past 50, then 100, then 150, the gathered ground crew stopped their routine tasks and simply stared. They'd patched bombers before. They'd replaced sections of damaged framework, recovered torn fabric, and repaired shot-out instruments. But they'd never seen anything survive this level of destruction. The final count, completed at 04:15 hours after 3 separate verification passes to ensure accuracy, came to 203 separate penetrations. 87 machine gun rounds had passed completely through the fuselage without hitting anything structural. They'd entered one side, flown through empty space between geodetic members, and exited the other side. 41 rounds had struck geodetic framework members directly, severing 11 of them completely and cracking or denting 30 others. 19 cannon shell impacts had created larger damage zones where explosive force had bent or broken multiple members simultaneously. The remaining 56 holes came from flak fragments that had peppered the rear fuselage and tail section. What astonished the ground crew wasn't just the quantity of damage, but its distribution relative to critical systems. The control cables running through the fuselage to the tail surfaces had escaped completely unscathed, despite being surrounded by bullet holes. The main fuel tanks positioned in the wings behind geodetic framework had been punctured in 3 locations, but the self-sealing rubber bladders had done their job preventing catastrophic fuel loss. The electrical systems were partially compromised, hence the failed instruments, but backup systems had maintained control surface operation throughout. The hydraulic lines to the turrets had been severed, but the turrets themselves remained mechanically sound. Chris walked around the Wellington twice, examining the damage from every angle, trying to reconcile what he was seeing with his understanding of structural engineering. By every conventional assessment, this aircraft should have broken apart over Germany. The sheer concentration of hits should have severed enough load-bearing members to cause progressive structural failure. Yet here it sat, geometry intact, framework solid, fundamentally airworthy, despite looking like it had flown through a hailstorm of steel. Chris made a decision that would have seemed reckless to anyone unfamiliar with geodetic construction. Rather than tagging the Wellington as Category 3 damage requiring depot-level repair, which would remove it from operational status for weeks, he classified it as Category 2, repairable at station level within 48 hours. His reasoning was simple. Despite the spectacular damage, no primary structural failure had occurred. The geodetic framework, though punctured and partially severed in multiple locations, retained sufficient integrity to support flight loads. More importantly, Bomber Command needed every available aircraft for tomorrow night's operation. Losing a Wellington to lengthy repairs meant 1 fewer bomber over Germany, 1 less contribution to the strategic offensive that everyone knew must be maintained regardless of cost. The repair crew assembled around the aircraft numbered 14 men, riggers, fitters, electricians, and armourers, pulled from other tasks or roused from brief sleep. They had approximately 4 hours to return this bomber to operational status before dawn made continued work visible to potential reconnaissance aircraft. The repair process began with structural assessment. Teams examined every severed or damaged geodetic member, testing adjacent members for hidden cracks or deformation. Where single members had been completely severed, the solution was surprisingly straightforward. Cut away the damaged section, splice in a replacement piece using fish plate reinforcements riveted on both sides, then stress test the repair by applying calculated loads. This was where geodetic construction demonstrated advantages that Wallis had promised, but skeptics had doubted. In a traditional longeron structure, replacing a damaged primary member required disassembling large sections of fuselage to access the component, then carefully aligning the replacement to maintain precise load paths. Geodetic members, by contrast, were individually accessible. A fitter could reach any damaged member without disturbing adjacent structure, cut it away, and install a replacement within 20 minutes. The repair didn't need to restore the member to original strength. It only needed to carry its share of distributed loads, which represented a fraction of total structural requirements. The fabric covering posed different challenges. Standard repair procedure called for cutting away damaged fabric in neat geometric shapes, then applying doped fabric patches that overlap the cut edges by at least 2 in. The dope, a cellulose solution that shrank as it dried, would tension the patch and bond it to the underlying framework. For small holes, this worked perfectly. For the Wellington's extensive damage, the crew made pragmatic decisions. Where holes were smaller than 6 in and positioned over solid framework, they patched them individually. Where fabric had been shredded across large areas with no underlying damage, they cut away entire panels and replaced them with pre-cut sections from the station's fabric stores. The electrical systems required meticulous cable-by-cable assessment. Each severed wire needed identification, testing for continuity on both sides of the break, then splicing with proper insulation and securing to prevent chafing against sharp metal edges. The wireless operator's position had sustained particularly heavy damage to communications cables, requiring replacement of a complete harness. 16 individual wires bundled together and routed through the geodetic framework to the radio equipment. An electrician spent 90 minutes on this single repair, working by torchlight in the confined space, testing each connection before moving to the next. By 0500 hours, the structural repairs were substantially complete. 11 geodetic members had been replaced, 32 had been reinforced with fish plate splices, and the framework had been stress-tested by loading sandbags onto the wings and fuselage whilst measuring deflection. The measurements matched calculated values for undamaged structure, confirming that the repair had successfully restored load-bearing capacity. Fabric patches covered 197 of the 203 holes. 6 holes in non-critical tail areas were left unpatched under the reasoning that they didn't affect structural integrity or significantly increase drag. At 2,000 hours on the 6th of April, barely 17 hours after Ward had landed the shredded Wellington, a different crew completed their pre-flight checks on the same aircraft. Pilot Officer Robert Chen and his navigator, bomb aimer, wireless operator, and 2 gunners had been briefed for that night's operation against KE's naval shipyards. They'd been assigned Wellington registration. R. Robert recently returned from repairs. Nobody mentioned that those repairs had been completed approximately 3 hours earlier, or that R. Robert had absorbed 203 bullet and shell strikes less than a day ago. Chen noticed the fresh fabric patches immediately. They were visible as slightly lighter rectangles against the original covering, and there were dozens of them scattered across the fuselage and wings. A few unpopular holes in the tail section remained visible, the torn fabric edges fluttering slightly in the evening breeze. He walked around the bomber slowly, running his hand over patch after patch, then looked at Hricks with a raised eyebrow. The crew chief's explanation was admirably succinct. She took some punishment last night. We've checked every structural member, replaced what needed replacing, and tested the whole assembly. She's as airworthy as any Wellington on this station. That assessment, delivered with absolute confidence by a man who'd been maintaining bombers since 1938, satisfied Chen. He'd flown Wellingtons for 6 months and understood their construction well enough to appreciate what geodetic design meant for survivability. The visible patches actually reassured him. They proved the aircraft had already survived severe punishment and returned intact. If anything, R. Robert was now the most thoroughly inspected Wellington at Mildenhall, every component having been examined and tested within the past 12 hours. The crew boarded at 205 hours. Chen started the engines, completed his checks, and taxied to the runway without any indication that R. Robert handled differently than any other Wellington. The repairs had restored the aircraft to standard configuration. Control surface response was crisp and immediate. Engine performance matched specifications. The compass, replaced entirely with a unit salvaged from another aircraft, provided accurate headings. As Chen advanced the throttles and felt the Wellington accelerate down the runway, he experienced the same confidence he'd felt on his previous 21 operations. This was a solid, reliable bomber that would bring his crew home. R. Robert lifted off at 20:37 hours and climbed into the gathering darkness. Chen joined the bomber stream heading toward Kiel, navigating by the standard route that would take them across the North Sea, over the Danish coast, then south to the target. The wireless operator tested his equipment and found everything functional. The replaced cable harness performed flawlessly. The rear gunner traversed his turret through its full range, confirming that hydraulic repairs had restored complete freedom of movement. Every system operated exactly as designed. The significance of what was happening didn't require explanation to anyone familiar with wartime bomber operations. RAF Bomber Command faced constant pressure to maintain sortie rates, despite inevitable aircraft losses and battle damage. Every bomber grounded for repairs meant reduced pressure on German industrial targets, giving enemy factories additional time to produce the weapons, killing British soldiers and civilians. The ability to repair severe battle damage at station level within hours rather than weeks represented an enormous operational advantage that directly translated to sustained bombing campaign effectiveness. Our Robert's rapid return to operations validated everything Barnes Wallis had claimed about geodetic construction's field repairability. The framework's modular nature meant damaged components could be individually replaced without affecting surrounding structure. The fabric covering, though vulnerable to puncture, could be patched quickly using materials and skills available at every bomber station. Unlike all metal-stressed skin designs, where damage often required specialized depot facilities and extended repair times, geodetic Wellingtons could be comprehensively repaired by station-level ground crews working with basic tools and standard supplies. Chen crossed the Danish coast at 2200 hours, our Robert performing flawlessly. The patches didn't whistle or flutter. The repaired framework carried flight loads without any detectable weakness. Somewhere below in the darkness, German night fighters were taking off to intercept the incoming bomber stream. Their pilots confident that fabric-covered British bombers would disintegrate under concentrated fire, a confidence that would cost them dearly. The incident report filed by Hricks on the 7th of April 1941 circulated through RAF Bomber Command with unusual speed. Air Marshal Arthur Harris, then serving as Deputy Chief of Air Staff before assuming command of Bomber Command in 1942, specifically requested detailed documentation, including photographs and structural analysis. What made this particular Wellington survival noteworthy wasn't that it had absorbed battle damage. Many bombers did, but the sheer concentration of hits combined with the rapid return to operational status. The report became required reading at RAF technical training schools where instructors used it to illustrate geodetic construction, principles to skeptical engineering students who still believed metal-stressed skin represented the future of aviation. By mid-1941, enough similar incidents had accumulated that Bomber Command's Operational Research Section conducted formal analysis comparing Wellington loss rates to other bomber types under equivalent combat conditions. The data revealed something remarkable. Wellingtons encountering German fighters returned to base 63% of the time, compared to 41% for Whitleys and 37% for Hamptons. When analysis isolated cases involving extensive battle damage, the disparity widened further. Wellington survived catastrophic damage at nearly twice the rate of conventional designs. This wasn't subjective pilot opinion or anecdotal evidence. It was statistical validation of geodetic construction superiority for combat survivability. German intelligence eventually recognized their fundamental misassessment. Luftwaffe technical bulletins issued in late 1941 revised guidance for engaging. Wellingtons acknowledging that British geodetic construction provides unexpected structural resilience requiring modified attack doctrine. Night fighter pilots received new instructions emphasizing sustained fire aimed at engines and cockpit rather than brief fuselage bursts. But this tactical adjustment came too late to prevent hundreds of Wellingtons from limping home with damage that doctrine had insisted should be lethal. The broader lesson that fabric covering over sophisticated framework could outperform solid metal construction challenged assumptions that had guided German aviation engineering for a decade. The Wellington's combat record influenced post-war bomber design in ways that weren't immediately obvious. No major post-war bomber adopted geodetic construction directly. The method was too labor-intensive for mass production and offered diminishing advantages as jet engines eliminated the weight efficiency requirements that had made it attractive for piston-engined aircraft. But the principle of distributed load paths and redundant structure became fundamental to military aviation design philosophy. Modern aircraft incorporate multiple redundant systems specifically because the Wellington proved that survivability depended on ensuring that damage to any single component couldn't cause catastrophic failure. Contemporary combat aircraft like the American A-10 Thunderbolt, designed 4 decades after the Wellington, embody lessons learned from geodetic construction without replicating its specific implementation. The A-10 features redundant flight control systems, engines separated to prevent single-point vulnerability, and structural design that tolerates severe damage to non-critical areas. All principles demonstrated by Wallis's basketweave framework. Military aviation had moved beyond asking how do we prevent damage to asking how do we ensure damage doesn't prevent mission completion, a philosophical shift that the Wellingtons' combat record accelerated. Barnes Wallis received a knighthood in 1968, honoured primarily for his work developing the bouncing bomb used in the Demusters raid. But his geodetic construction system arguably saved more lives and contributed more significantly to Allied victory than any single weapon design. 11th Hour 461 Wellington served with Bomber Command during the war. Statistical analysis suggests geodetic construction's superior survivability prevented approximately 2,300 additional aircraft losses compared to equivalent numbers of conventional bombers, representing roughly 13,800 aircrew who came home because their aircraft refused to break apart when physics and German engineering insisted they should. That Wellington sitting at Mildenhall on the 6th of April, covered in patches and ready for another mission, represented more than one aircraft's survival. It represented vindication of a design philosophy that prioritized resilience over rigidity, distributed strength over concentrated robustness, and ultimately proved that sometimes the most sophisticated solution looks deceptively simple, like a woven basket wrapped in Irish linen, holding together against impossible odds through pure mathematical elegance.